Here we are with the formal definition of a limit. Now, a limit exists if and only if both the left side and the right side limit exists, and that's the first criteria. So if both corresponding limit exists, and those have to be meeting up at the exact same spot. In other words, they have to be equal. So in terms of the mathematical notation, how that looks is if we have the limit as x approaches some constant value of a particular function, f of x, is going to be equal to some limit if and only if the limit as x approaches some constant from the right of our function is equal to some limit, which happens to also be equal to the limit as x approaches some constant from the left of our function. So as long as our limit as x approaches some constant from the right of our function is equal to some limit, and it also happens to match it from the left side, then our limit actually exists. It doesn't exactly say where it is, however, it is stating that it will in fact exist. Okay, and then when you're saying that it does in fact exist, you can then start to say, okay, this is what it is, by doing various techniques. Now when we look at example 5, we're asked to evaluate the following limit. The limit as x approaches -3 of this particular function. Now we can go ahead and relate this definition with example 5 when we see that we're asked to evaluate this following limit. The limit as x approaches -3 of this particular function. Well, if you were to try direct evaluation and pretty much just throw this value in, you would end up with a 0 over 0 indeterminate form. So that just won't quite work out. Another option that we can go ahead and do then is our factoring method. Now I'm going to go ahead and show the factoring method using both the left and right-sided limits. So for the first one, we have the limit as x approaches -3 from the left of our particular function. And as we said, we can go ahead and factor out something. It looks like we could pull a 3 out of this top guy. So we'd be left then with 3 times x plus 3. On the bottom, we see that that is the difference of two perfect squares. So that's x plus 3 times x minus 3. And we can see that our x plus 3's end up dropping out. So then we're left with the limit as x approaches -3 from the left of 3 on top still over x minus 3 on the bottom. Well, going ahead now and plugging that value in, we end up with -1/2. So that's all great. We took care of the left-sided limit. Let's go ahead now and try the right-sided limit. So this is for left again. For right. We then end up with the limit as x approaches -3 from the right. Again, we're going to pretty much just follow the same exact algebraic steps, but this is kind of the small proof on why it actually works out. On the bottom, you still factor that x plus 3 times x minus 3. X plus 3's end up canceling out. We're then left with the limit as x approaches -3 from the right of 3 on top over x minus 3. And if you were to plug in -3, even though it has that little plus sign, doesn't really matter or affect things too much when we're talking about algebraically finding a limit, we end up with 3 over -6, which again comes out to be -1/2. So because these guys are actually end up matching at the same spot, we do know that our limit is going to exist. We can even look at our table of values as you approach -3 as well. So here is -3 from the left side. You know, you're getting closer and closer and closer to -3. It appears that our values are getting closer and closer and closer to negative 1/2. Whereas if you're approaching negative 3 from the right side, again, these are values a little bit closer to negative 3 from the right, we notice that our values again are getting closer and closer and closer to negative 1/2 as well. So our final answer, and especially how this relates with our definition, is since both the left and right-sided limits are going to negative 1/2. So pretty much the limit as x approaches negative 3 of our function f of x is equal to then negative 1/2. Alright, so again, we're proving that the left side is going to negative 1/2, we're proving the right side is going to negative 1/2. Then because they are both matching up, this again was the algebraic proof behind it. This is like using the data, and this is looking at the graph. I kind of wanted to show all three aspects so you guys have a wide variety of things to look at and see why things are working. But again, that's really how it ties with this definition as well. We can state then that the limit as x approaches negative 3, both left and right, of that function is going to negative 1/2. All right. So again, that is the formal definition of a limit and example 5 from the 1.2 set of notes.